Hi, everybody. I hope you had a great weekend. It's a little bit awkward. I just realized when I was looking at the next chapter that we already covered everything that was in that chapter. So today's video lecture is crazy short. I'm just going to take a look at two of the more difficult questions you had on your assignment sheet for tonight. Take a look at number 66. At a certain factory, 300 kilogram crates are dropped vertically from a packing machine onto a conveyor belt moving at 1.2 meters per second. A motor maintains the belt's constant speed. The coefficient of kinetic friction between the belt and the crate is 0.4. 0.4. After a short time, slipping between the belt and the crate ceases, and the crate then moves along the belt. For the period of time during which the crate is brought to rest relative to the belt, in other words, moving with the belt, calculate for a coordinate system at rest in the factory, the kinetic energy supplied, the magnitude of the kinetic friction, the energy supplied by the motor, and then explain why answers might differ. All right, so first of all, take a look at the crate. We've got a kinetic friction force acting this way because initially they hit this thing stationary. And remember, friction always acts against the slide or potential slide. And you'll notice the conveyor is moving this direction. And so the tendency would be to slide or stay in place. And so friction's actually acting forward. And it's going to actually gain kinetic energy because of this. If you calculate the kinetic friction just real quick, you'll discover that, remember, it's mu sub k times normal force. In this case, mu sub k is that. Normal force, just the 300 times 9.81, gives us that to 3 sig figs. And the kinetic friction to 3 sig figs is 1180. So that's the force acting forward. All right. So first of all, what's the change in kinetic energy? Well, it starts out with none horizontally. And so the ending part is just 1/2 its mass times its final velocity squared, or 432 joules. You're like, hey, that's easy. B, the magnitude of the kinetic frictional force, we actually already solved that. So just that 1180. And then C, the energy supplied by the motor. So the energy supplied by the motor is the work done on the crate. Now this gets a little bit more complex. First of all, figuring out the acceleration of the crate, that force equals the mass times the acceleration, we get that. Calculating the distance the crate slides on the belt before it comes to a stop, final velocity is 1.2, initial velocity is that, 2 times the acceleration times delta x. We'll discover it slides that far relative on the belt before it reaches its final velocity. Calculating the work done by the motor, that's just the force dot delta x, force it had to exert times the distance it slid, 216 joules. Now, why is this different than the gain in kinetic energy? It looks like somehow we've cheated, that the motor actually didn't do as much work as we thought. Well, in reality, what's happening is this. The distance we calculated up here, this distance right here, is relative to the conveyor belt, not the reference frame of the factory floor, which is what we were told to use. Because the belt was moving, the crate actually slid this far relative to the factory floor. If you calculate the acceleration, you calculate the time it took, and you can calculate the extra distance then that the belt moved relative to the factory floor. And if you take this distance times this force, believe it or not, you will end up with the same energy. Yes, the motor really does all the work required to bring it up to that speed. All right. And the other one I wanted to take a look at is 71. 71, a conservative force acts on a 2 kilogram particle that moves along the x-axis. The potential energy graph associated with it is graphed to the side. When the particle is at 2 meters, its velocity is negative 1.5 meters per second. What's the magnitude and direction of the force at this point? Between what positions on the left and right does the particle move? In other words, where is it trapped? And what's the speed when the particle is at x equals 7 meters? All right. First thing, whenever you get a graph like this and we're given a point, let's figure out the total energy of the particle. Total energy is kinetic energy plus potential. And we're told that the instant it's at this position, we're told its velocity is this. And we can read from the graph that its potential energy is roughly negative 7 joules. And so the total energy of our particle, negative 4.75 joules. And that's got to be maintained. It's got to be consistent. Unless there's some sort of extra energy being pumped into the system, our particle is trapped because its total energy is that. Calculating the slope at this point, if you draw your line right here, you'll discover that the slope is negative 5. So that's du dx. And remember that negative du dx is equal to our force. So negative 5 is equal to negative F. And so our force here is positive 5 newtons. What's its direction? Because it's positive, our force in this case is acting towards the positive x direction. Our particle wants to go back this direction. And finally, what are the limits? If our total energy is this, we're limited to roughly here is where its potential energy is negative 4.75 on the wrong side here. Sorry, right there. Not that one. And right here. It can't go beyond that. If it did, the potential energy would be like negative 2, which means our kinetic energy would have to be negative. And so roughly on this side, that's about, and I'm calling it about 1.5. If you looked at the graph really closely, you can get probably a better answer to that one. And then on the other side here, that looks like it's about, wait a second, interesting. On the other side, I said roughly about 14 meters. At those 2 points, the kinetic energy drops to 0, and the object can't travel any further. It's trapped between these 2 positions. It can go here to here, but at this point, the kinetic energy and the velocity is 0. Here it's 0. And so our final question asks, what is it at x equals 7? So if you work down here at x equals 7, its potential energy is negative 17 joules. And so solving this, we know the total energy is this, and that has to equal kinetic energy plus potential. And at the point we just talked about, the potential energy is negative 17. And so now if you solve this for velocity, you'll discover the velocity is roughly 3.5 meters per second. Hopefully this will get you started. I know this is a relatively short video. That's all right for a change. Hopefully you'll have no problems with the homework. Start taking a look at the review. I will poll you in just a few minutes to ask you if you think we should have a live review day session. It'd be good to get the class together. Have a good night, and we'll talk to you soon. Bye.